Suppose we have a function, let's say f of x equals to 1 divided by x, and we want to compute the area under the curve in a particular interval, in this case between 1 and 6. Integration tackles this particular problem and will be the main focus of today's video. Many of you may already know the general idea behind computing the area under a function, that is, computing the definite integral of a function. If not, let's just take some rectangles over our interval to illustrate it. One can see that the rectangles approximate the area. As the area of the rectangles can be calculated quite easily, this seems as a good way to start. Let's now make the rectangles thinner, that is, let's add more rectangles over the interval. As more rectangles are added, the area of all the rectangles combined gets closer to the area under the curve. If we take the limit as the width of the rectangles goes to 0, or similarly, the limit as the number of rectangles goes to infinity, then the area of the rectangles approaches the area under the curve. The limit of the sum of the area of the rectangles as the number of rectangles tends to infinity may in itself be taken as a definition of definite integral. However, today we will be explaining a slightly more rigorous way of defining the integral. This will be indeed more challenging, but will provide us with a deeper understanding of the process of integration and will make integration itself a much more powerful mathematical tool in our repertoire. Nevertheless, this reasoning will still be helpful as a starting point in our search for a formal definition of integration. We will now take a closer look at the process of forming the rectangles. As we have seen in these animations, the rectangles have a particular width. This width, to be more general, does not necessarily have to be the same for each rectangle. Thus, each base of the rectangle occupies a particular subinterval inside the interval for which we want to calculate the area. This is where partitions come into play. Given an interval AB, we can construct a partition P of the interval as seen. The numbers x2, x3, and so on between A and B will just form subintervals inside the interval AB. A possible partition, for example, of the interval 1, 6 could be the set 1, x2, x3, and 6, where x2 is greater than 1 but less than x3, and x3 is less than 6. As seen in the graph, this would just form subintervals that we could take as the basis of our rectangles. Now that we know how to form the basis of our rectangles by taking the base to be the length of a subinterval in the partition, let's now try to understand how we can construct the rest of the rectangle. We will illustrate this with a particular subinterval from x2 to x3. We want the area of the rectangle to approximate the area under the curve. Hence, the height of the rectangle must be a value of the function. However, this leads us to infinite possibilities for the height of the rectangle. We could take, for example, the height of the rectangle to be the maximum value of the function in this subinterval. In this case, it would be f of x2. Then the area of the rectangle, we will denote it as upper area, a sub u, would be the height, f of x2, times the width, x3 minus x2. Other possibility is taking the minimum value of the function as the height of the rectangle, in which case the height of the rectangle would be f of x3, and the area, which we will denote as lower area, a sub l, would be the height f of x3 times the width of the rectangle, x3 minus x2. We could even take the height to be the value of the function at the middle point, as this seems to be a better approximation. Anyhow, we will focus in the limiting cases, that is, for the maximum and minimum possible area of the rectangles, such that we still approximate the area under the curve. How can we create a rectangle with the maximum area for a given interval? Well, the base is already fixed. So we have to look for the maximum possible height denoted by uppercase mk. This is best characterized with the supremum. By taking the supremum of the set f of x such that x is in our interval, we assure that the height will be maximum. Recall that a supremum is defined as follows. S is the supremum of a set A if, firstly, all elements in the set A are less than or equal than S, that is, S is an upper bound for the set A, and also if B is an upper bound as well, then B is greater than or equal than X. In a way, with the supremum we are making sure that we get a value which is greater or equal to all the elements of the set, but that it is also as close to the set as possible. This last fact makes us approximate the function. Note that the supremum of a set may not be contained in the set, so now the height of our rectangle may not be a value of the function per se. Thus, our value of the maximum area we have found will be the maximum height, that is uppercase mk, times the interval xk minus xk minus 1. If we take a look at the previous example, the supremum of the set f of x such that x is in the interval from x2 to x3 is indeed f of x2, as the function is decreasing and continuous. Therefore, the maximum possible area will be f of x2 times x3 minus x2, as our intuition firstly thought. Now, in the reasoning, we have only taken into account one of the subintervals of the partition. And what we really want to do is to make the same process for all the subintervals of the partitions. This is defined as the upper sum, and is just the sum of all the areas of the rectangles that we have defined this way in the partition. We can see that for the subintervals of the partition we are calculating the area of the rectangle with height uppercase mk and then summing all together. Clearly, the upper sum depends on the partition of the interval we are working with. The same reasoning can be replicated to find the smallest possible area of the rectangle. To do this, we have to look for the minimum possible height, denoted by lowercase mk, which will be characterized by the infimum. By taking the infimum of the set f of x such that x is in our interval, we assure that the height will be indeed minimum. Recall that an infimum is defined as follows. I is the infimum of a set A if, firstly, all elements of the set A are greater than or equal than I, that is, I is a lower bound, and if B is also a lower bound, then I is greater than or equal than B. In this case, with the infimum, we are making sure that we get a value which is less than or equal to all the elements of the set, but that it is also as close to the set as possible. Thus, our value of the minimum area we have found will be the minimum height, that is lowercase mk, times the length of the interval, xk minus 1. If we take a look at the previous example, the infimum of the set f of x such that x is in the interval from x2 to x3 is indeed f of x3, as the function is decreasing and continuous. Therefore, the minimum possible area will be f of x3 times x3 minus x2. Now we want to make the same process for all the subintervals of the partition, so we can find the lower sum. This will be the sum of all the areas of the rectangles that we have defined this way in the partition. We can see that for the subintervals of the partition we are calculating the area of the rectangle with height lowercase mk and then summing all together. Now that we have defined upper sums and lower sums, it is useful to find the relation between them. This is not at all difficult. Take a partition P of an interval. We know that the supremum of a set has to be greater than or equal to the infimum of the same set. This is the same as saying that uppercase mk is greater than or equal to lowercase mk, which clearly implies the following inequality regarding the sums. This can just be rewritten as the fact that the upper sum of f with respect to a partition P is greater than or equal to the lower sum of f with respect to the same partition P. Furthermore, we know that the upper sum must be greater than or equal to the area of the curve. and the lower sum must be less than or equal to the area below the curve. So we arrive at the following inequality. This inequality shows that maybe a way of finding the area is making the upper sum lower and the lower sum higher, as then both these extremes of the inequality would approach the area. To do this, we must first understand the concept of partition. Let P and Q be partitions of the same interval. We say that Q is a refinement of P if P is a subset of Q. For example, if we have the partitions P equal to the set containing the elements 1, 2, 3 and Q equal to the set containing the elements 1, 2, 3, 4, we say that Q is a refinement of P, as the set P is a subset of Q. It can be understood as that to form a refinement we have to add more subintervals in the partition, that is, include more elements in the set. Considering this, we arrive at the following lemma that states that if the partition Q is a refinement of the partition P, then the lower sum of F with respect to P is less than or equal to the lower sum of F with respect to Q. On the other hand, the upper sum of F with respect to P is greater than or equal to the upper sum of F with respect to Q. What this says is that if we add more elements to a partition, or similarly increase the number of subintervals, that is, the number of rectangles, then the lower sum increases and the upper sum decreases, just what we wanted. We are not formally going to prove this lemma in the video. I leave this as an exercise for you, but we are going to illustrate this visually to try to understand why the lemma is true. Suppose we have a function with a partition P and xk minus 1 and xk are successive elements of the partition. While computing the upper sum of the function with respect to the partition P, we will have to find, as we called it earlier, the maximum area of the rectangle that approximates the area under the curve on the interval xk minus 1 to xk. To do this, we compute the supremum of the function on this interval, and the area results to be the rectangle shown. Now suppose we add one element set to the partition that lies between xk minus 1 and xk. Then we have two subintervals, and we will have to do the same process separately for these two subintervals, as part of computing the upper sum. One can clearly see that when we add the element set to the partition, the area of these two rectangles combined is less than the area of the first rectangle without the element set. This shows that when we form a refinement by adding set to the partition, the upper sum decreases. Similarly, for the lower sum without set, the infimum would be f of xk minus 1, so the rectangle would be as shown. When we add an element set to the partition between xk minus 1 and xk, one can clearly see that the combined area of these two rectangles is greater than the area of the previous rectangle. Therefore, when we form a refinement, the lower sum increases. Now that we have found a way in which we can make the upper sum decrease and the lower sum increase, we are ready to define the Riemann integral. Assume the function f is bounded. We will denote by this tilted p the power set of the partitions of AB. That is, the collection of all the possible partitions of AB. We will define the upper sum of f, u of f, as the infimum of the set containing the upper sum of f with respect to all the possible partitions of AB. Similarly, we will define the lower sum of f, L of f, as the supremum of the set containing the lower sum of f with respect to all the possible partitions of AB. These are the best approximations for the area from above and below. We have made the upper sum as small as we can approaching the area from above, and we have made the lower sum as big as we can approaching the area from below. Therefore, in the case where UF and LF exist and are equal, we say that the function is integrable on the interval ab, and we denote this as follows. Therefore, in order to compute the integral with this definition, we would have to compute u of f and L of f, and if they are equal, the integral will exist and will have value of u of f, or what is the same, L of f. Obviously, there are easier ways of computing integrals, but this definition has a lot of power, as with it we can check if a function is integrable, and we can also find the definite integrals for some very interesting functions. But that for another video. Stay tuned.